Okay, so let's start. Welcome everyone. So we are in lecture 14. I think we have only a couple of lectures left. And let me kind of summarize where we are and what we went through. So I remind you that in what we started in the last class was we were applying the theory of open quantum systems to atomic processes and in particular to spontaneous emission. So let me just remind you. So what we have in this case, it's an atom that it's essentially in free space, and then it's coupled to the electromagnetic field of free space. So just like in the cavity, that we had a cavity that was coupled to the external modes of the cavity through a partially transmitting mirror, here we also have that the atom is coupled to a continuum of modes, but now the modes of the electromagnetic field, the ones moving to the right and the ones moving to the left, are independent, and this shows up in the expression for the quantum electric field, in which you see that now the annihilation and creation operators are labeled by the wave vector that has a sign. It can be positive or negative, and different wave vectors are independent, okay? So they form a canonical commutation relation algebra as a function or in terms of the label. So then what we saw is that essentially we can do a model of the whole universe, so the atom and the environment, that is a free electromagnetic field, in which we have just our two-level atom that has this Hamiltonian, then our electromagnetic field that has this Hamiltonian, so frequency, sorry, energy h bar omega for each of the oscillators with wave vector k. And then we have an interaction, and this interaction we wrote in this way. And then now we simply proceed in the Schrodinger picture to find a master equation for the atomic system only, okay, a reduced master equation. Then what we discussed last week, and today we will generalize it, is that essentially, if we make the same approximations that we made in the open cavity, and we essentially made 3 approximations or 2 approximations and 1 assumption. So the first approximation is that the coupling doesn't depend on the wave vector or the frequency, so it's just some constant. And then we make also the approximation that the integration over frequencies, okay, we can extend it to minus infinity, because we know that only the ones that are resonant, only the frequencies which are around the atomic transition will contribute to the physics. And then we can essentially extend mathematically to minus infinity. And as I told you, do not confuse the integrations over frequencies that are extended to minus infinity with the original integrations over wave vectors that are really from minus infinity to infinity. And in this case, k is really a physical, negative k is really a physical quantity, so it's a negative momentum. However, we will use also today that whenever you have a kernel that is symmetric under exchanges of the sign of k, so it depends only on the absolute value of k, then these integrations over wave vectors, they can be written as 2 times integrations over frequencies, or positive wave vectors. And at the end, we can rewrite everything as 2 times integrations over frequencies extended to minus infinity. Okay. Then, as we saw with the cavity, we expect that these 2 approximations, okay, will imply Markov. So will imply that at the end, we will get a time local master equation without having to invoke any more approximations. And then finally, assuming that the thermal, so that the environment is in a thermal state, possibly with some lasers that we add, and using the Born Markov approximation, the Born and absence of back action from the system, so from the atom to the big environment, then we find a master equation that looks very similar to the one that we saw for the cavity. In particular, we have the free Hamiltonian term, then for the atom, then we have some injection term that comes from the laser. So, and it has this expression. And then we have the thermal part, or the part coming from the thermal environment, from exchanging excitations with the thermal environment, in which essentially we have the same as in the optical cavity, but replacing the annihilation and creation operators by the raising and lowering. So raising and lowering operators, okay? Just like in the injection Hamiltonian is the same, okay? So essentially, this is the master equation that we write down for an open atom. Maybe I take the opportunity just to let you know that in the final exercise that I will ask as homework, which I will probably share it later today, you will see that there is one more process that plays a role in atomic incoherent processes, which is called dephasing, okay? And you are going to kind of find what is the master equation associated to the process of dephasing. And you will also have the chance of learning something new, which is that instead of finding a master equation in the situation in which you have one small quantum system interacting with a bigger quantum system and then tracing out the big quantum system, what you will see in the exercise is that the same kind of master equations, okay, the same kind of form, you can find whenever you just have classical noise in your system. So something is fluctuating randomly in your system, and this brings, assuming certain conditions, again, Markov approximations and so on, that you bring in this kind of dissipation terms, okay? So this you will learn in the exercise, which will be the last exercise that I will ask for you to hand in. And then, but what we did last week was studying this master equation that has only this process of interaction with the environment and exchanging excitations. So in particular, what we studied is that when we don't drive the cavity, so when we don't add any lasers, and when we have zero temperature, so the environment is at zero temperature, then what we saw is what is the evolution of the atomic state. And in particular, what we saw is that the atomic state, so for long times, independently of what is the initial state of the atom, it will end up in the ground state, okay? And this is a process that we call spontaneous emission, okay? And going into a bit more detail, we studied one specific case in which we start with a pure state for the atom. In particular, we put it in the excited state, and then we let it evolve, okay, according to the master equation. And what we found is that the state of the atom at any time, it can be written as a mixture, okay, and with a probability that decays exponentially with time in the excited state, okay? Then this means that essentially for long times, so at time infinity, you end up in the ground state, but for intermediate times, so you always have a mixed state, and in particular, at some specific time, so let's say in the middle of the evolution, you get the maximally mixed state. So this problem is very interesting because it allowed us to also solve it analytically in the sense that we find what is the state of the whole universe, so the environment plus the atom, okay? And this is what we did at the end of the class, and what we saw is that you can write for a situation, of course I'm talking of a situation in which you start with no photons in the environment and just the atom in the excited state, okay? So for that situation, you can write, because you have a single excitation in the system, you can write the state as a superposition of the excitation being in the atom or the excitation being in the field, okay? And in particular, with an amplitude beta that depends on the wave vector. So this is the probability amplitude for the photon to be at wave vector mode k at time t, okay? Then what we saw is that you can find an analytic expression at least under the kind of Born Markov approximation that we are working on. So at that level, you can find an analytic expression for this probability of the photon being in a mode with wave vector k. And what we discussed is a few properties of this. The first one is that it doesn't depend on the propagation direction, which is obvious, like if there is no preferred direction and you have available plus k and minus k modes, the atom will just emit a photon in a random direction, okay, with probability 1/2. And then what we also saw is that this probability for long times, so when the time goes to infinity, it just becomes a Lorentzian, just like it happened in the cavity, in the optical cavity. And in particular, this Lorentzian in this case is a Lorentzian that allows us to see that all the approximations that we made of resonant processes and Markov and so on, they are kind of correct. So again, the atom can only emit photons that have frequencies that are around the optical transition, and around meaning within the line width. That this gamma is usually called the line width of the transition, of the atomic transition. Okay, then of course we also saw that the amplitudes are normalized, and then essentially because we have the analytic expression for the state of the whole system, this allows us to see that at any intermediate time, the state is an entangled state between the atom and the field, okay? And of course, if you trace out the light field, so the electromagnetic field from this state, then you end up with the same kind of mixed state that we found from the master equation, okay? So I think that this is everything that we saw. And then what we are going to do today is we will continue with this kind of incoherent atomic processes, but we will kind of extend the theory of open systems to situations in which the coupling might depend on the frequency, okay? So let me just dive into it. So this is section 3 of section B of this chapter. And then the question that we are going to answer in this final section is the following. So the question is, what happens if we cannot make the flat coupling approximation? So the approximation in which the coupling is just assumed to be independent of the frequency or the wave vector. And also we cannot make the approximation that we extend the integrations over frequencies to minus infinity. Okay, so what if we cannot do these approximations? Can we still proceed? Do we need some extra approximations to find a master equation? So in order to answer this question, let me come back to the expression of the evolution of the reduced state of the atom right after doing the Born and the absence of back action from the atom to the environment approximations. So let me write it down and you will hopefully remember what I'm talking about. So I'm talking about this expression in which the evolution of the atomic state in the interaction picture is given by an expression that is explicitly second order in the interaction, and in particular it looks like this. It's an integral differential equation that it's a double commutator of the interaction Hamiltonian at 2 different times. And now the state, but we already make the Born approximation, which means that now we already have here the atomic state tensor product with, sorry, this is in K because now we have Ks. And here the thermal state, but I will assume for simplicity that we are at 0 temperature. So we are in the vacuum state of the external or the environmental modes, okay? So I hope that you remember that after Born and Markov approximations, this is the exact form that we found for the master equation. So exact within those approximations. And then, yeah, I need to give you also the interaction picture Hamiltonian for the atomic case. And in particular, we have this expression. So we have IH bar, then integration decay, and yeah, so let me write down that in here we have, well, let me write in general the coupling of K, and then a dagger of K, sigma. And now we assume that we have no lasers either. So all the atomic Hamiltonian is just the free evolution of the atom. And then in that situation, you get here a factor that reads like this. Okay? So this essentially describes the problem within the Born approximation. And now we are going to try to push the situation from here without assuming that G of K is independent of K, or that we can extend the integration over frequencies to minus infinity, okay? So, yeah, let me just point out one thing that Sijan already asked a few days ago, or I think it was in the last class or the previous one, which is the fact that we did the Born approximation and the absence of back action approximations because we wanted to truncate the evolution of this evolution to second order in the interaction. But then it's true that because this state still depends on previous times, essentially this state, okay, so this part of the state, it still has some dependence on the Hamiltonian, okay? In particular, if you want to evolve from time t to time t minus tau, you will have to apply the time evolution operator given by the interaction at time tau or minus tau, okay? So then essentially, if one thing that we could do right away is saying, oh, okay, so let's make the approximation that tau is equal to 0, okay? Because otherwise we end up with something that is not order 2 in the interaction, okay? So in principle, this is one way of arguing, and that's okay. But we are going to push it a bit more to understand exactly under which conditions we can actually make this approximation in which we put tau equal to 0, okay? And you will see that it's very natural. So then let me expand this expression. So I will not do any approximation yet. I will just expand this expression. So you might remember that here we have a double commutator, and the Hamiltonian has two terms, this and the Emission conjugate. So in total, we have here 16 terms or 16 traces, okay? However, out of the 16 traces, so out of the 16 terms that appear, we have only 4 terms that are proportional to the only second order moment that is non-zero, in the case in which the environment is in vacuum, which is this one in here. Okay. Oops, I forgot to add the. So this is the expectation value in the vacuum state. Okay. So we have only 4 that are proportional to this one that survive. And in particular, this allows you to write the master equation in a very simple and compact form, which looks like this. So let me write it down. So we have the time integral, then the k integral, which is proportional to the coupling square. And then we have here the operator part that looks like this. T minus tau, then sigma dagger, T minus tau, sigma dagger, sigma. Then we have the exponential of time, and the Emission conjugate of these expressions, okay? So in this case, we get 4 terms, and we only need to write 2 because the other terms are just Emission conjugates of these ones. Okay, but now we can do, so we can rewrite it in an even more compact form, which is the following. First of all, I will, let me see. Yes, so we can combine everything that has an integration over k, we can combine it together, okay? So you see that we have g that depends on k, and we have this part of the exponential that depends on k, and then the integration over k. All that we put together, and then we end up with an even more compact expression that looks like this. So perhaps I put the exponential first. This is minus I epsilon tau. Then a function that we call c that depends only on time. And then the same and the same operator term. So I will just copy and the Emission conjugate. Okay, and now what is this c? So what is this function c? So this is a function that contains all the integral parts. And as I already mentioned in the summary, we are always going to replace kind of integrals over wave vectors by integrals over frequencies, just by using this change of variable. And we can write the integration over wave vectors, then we can write it in terms of frequencies in this way. 2c g squared of omega divided by c, and then I omega tau, yes, because we have ck. So this is it. So just pay attention to what I did. I just changed the, well, gk depends only on the absolute value of k, and that's omega divided by c. Then the integration from minus infinity to infinity, I wrote it as 2 times the integration from 0 to infinity, and then I changed k by omega divided by c, and this gives me a 1 over c from the differential. So then at the end of the day, you have a function that looks like this. And the reason why I wrote it like this, it's because, as you will understand in a second, this contains all the information about the environment and all the information about the timescales of the problem that, that are relevant to understanding whether the Markov approximation can be done and things like this. So in particular, this function in here, it's so important that it receives a special name. This is called the environmental correlation function. So this is the correlation function of the environment. Okay. And most importantly, the kernel of the integral without the exponential part, so without, let's say, the transform part, this thing in here, usually it's called G of omega, and we call it spectral density. Okay, so in our case, we have one specific spectral density because we have the coupling G. So we know that the coupling G is the square root of the wave vector and some more factors. So we know that this G squared is essentially omega. However, this is very nice because you see now that all the information about the environment is contained into this spectral function, or all the information about the interaction with the environment is contained in this like spectral density. Okay, so then what you can do, or what people usually do in open systems, is that instead of having to find a microscopic model for the interaction between the system and the environment, you can just guess what is the spectral density of your environment, okay? Or if you want, you can just try different spectral densities and see if you get interesting physics with different spectral densities, and then try to come up in the lab with an environment that has that spectral density, okay? So this is one approach to open quantum systems that is very typical, that is just trying to engineer or model what is the spectral density of the environment instead of the microscopic interactions between the system and the environment. But in any case, you see that at our level, all these are just natural definitions that appear, and all the information about the spectral density, or if you want, the transform of the in time of this spectral density is contained in this correlation function that is essentially all that appears in the master equation for the system or for the atomic state. And let me then point out a few things. So the first one is that if we can make the approximation that this spectral density that appears in the correlation function is independent of the frequency omega, and we also know that the interaction, so let me write it like this, that the light matter interaction is much smaller than the free Hamiltonian, then so we can make the approximation that the integration can be extended to minus infinity in frequencies, okay? Then essentially you can show very easily, so I'll show you in a second, that the correlation function is proportional to a delta function in time, okay? So this is here. So if this is a constant, okay, if G of omega is a constant, and then you can put it out, and then you extend the integration to minus infinity, you end up just with the integration from minus infinity to infinity of this exponential, and that's the delta function of tau, okay? Now, when C is the delta function of tau, then you can remove the integral, like we have seen before. In time, you can remove it, you can put tau equals 0, and then you end up with the master equation that we discussed already. However, when this is not the case, so otherwise, then C of tau So if you cannot make that approximation, then C of tau, it's just half the Fourier transform of the spectral density. Okay, and this is the best that you can do. If you know the spectral density, you either numerically or analytically, if you are lucky, you do half the Fourier transform, you get a function that depends on time, okay? And then you get a master equation that will be time non-local, that will be non-Markovian or integral differential. However, if you know what is exactly the form of this C of tau, you might try to solve this equation, okay, integral differential equation, with Laplace transform techniques. Maybe you have heard of the techniques to solve differential equations based on the Laplace transform. And remember that this is very useful because it transforms, of course, derivatives into products, but it also transforms integrations on fractions. And therefore, you can rewrite the whole integral differential equation in Laplace space or with the Laplace transform as an algebraic equation. And then the only problem is to do the Laplace, the inverse Laplace transform to come back to real time, okay? However, so this is something that, for example, I have worked on as well in some of my papers, but in general, this is it's very complicated because first of all, you don't have the correct expression for C of tau most of the time. And second, because applying inverse Laplace transforms, it's a very complicated business. So then can we do something to simplify the problem? So actually, here is where the Markov approximation comes in, and let me explain it to you. So, so let's say the following. So imagine that, okay, you calculate C of tau, it's half the Fourier transform. And of course, you know that if G of omega, it's not independent of the frequency, but it doesn't depend so strongly on the frequency, meaning that it evolves or it changes slowly with the frequency, like for example, our square root of omega, which is not a function that oscillates very wildly in time or anything like that. Then you know that if when it is independent of the frequency, it was a delta function, which means that C of t decays to zero immediately, okay? So it's infinity at tau equals zero, and then it's zero right when tau is a little bit different than zero. Then what will happen when G of omega is dependent on the frequency, but not very strongly, is that C of tau will still decay in time, but with a width that now is non-zero, but maybe it's still fast enough to allow for some approximation. And in particular, the approximation is the following. So if C of t still decays faster than the rate of evolution of the atomic state, okay? And this rate of evolution, you can approximate it by the spectral function of epsilon, okay? Or if you want by what we define as gamma, more concretely, then we can do what we will call the Markov approximation, okay? Which is that we can approximate in the integral kernel, we can say that the state at time t minus tau, it's approximately equal to the state at time t, okay? So just let me go back to this for a second. So again, my argument is the following. This C of tau even when G depends on the frequency, so even when we have a spectral density that it's not independent of omega, if the dependency is not too strong, then it will decay in time, okay? And if the decay of this function is fast enough, so in particular, the decay of this function will determine how far away you can look into the past, okay? Or how far away the time derivative can look into the past of the state. So if that decay is very quick compared with the evolution scale, time scale of the state, then of course during that time the state will not have evolved, okay? So then you can make the approximation that tau is equal to 0 essentially, okay? Then if you make this approximation, and this is called the Markov approximation, then you end up with an equation that looks like this. So it's a little bit different than the master equation that we have been working with, the Markovian master equation that we have been working with. So let me show it to you. So we have an equation that looks like this, where this gamma t, it has this expression. So it's an integration in time, then an integration in frequencies of the spectral density. So it's essentially the integration in time of the correlation function, which putting everything together, we can write it like this. Okay? So this is the master equation of the reduced atomic state under the Markov approximation. Okay? So I hope this is clear. And then you see that applying this Markov approximation, we have found an equation that looks very similar to the master equation that we had within the previous approximations. However, now we have here some rates that are time dependent. They are not time independent. And moreover, in principle, they can even be complex. So there is nothing that tells you that this has to be real, okay? So, however, if the gammas would have a very weak time dependence or n will be real, then this equation is already a master equation like the ones that we have seen. Otherwise, we have these time dependent rates that we have to understand a little bit better, okay? So then you see that applying this Markov approximation and applying the approximation, these ones in here, that the spectral density is independent of omega and that the integration can be extended to -infinity, these two approximations are not exactly the same. So in particular, these approximations in here are stronger than the approximation that we call the Markov approximation, okay? So they are kind of a particular case of a Markov approximation, but the Markov approximation allows for more general things. So, and then now to finish, let me just discuss the form of these complex rates, okay? So in particular, you can prove it's not very complicated. So using, probably I will write it in the notes, using complex analysis techniques, in particular integrations over complex, the complex space and so on, that probably you have studied in math. You can prove that for long times at least. So for short times, we cannot say too much, okay, about this gamma of t. You can just evaluate it, get it, and see how it is. However, for long times, so in the limit when t goes to infinity, which is the limit in which we usually care about, as we have been discussing, Then you can write it in the following way, okay? As I say, this can be proven. There is no approximation. So this is in the limit of t going to infinity. There is no approximation apart from some physical assumptions about the type of spectral density that you can have, okay? So you can find that it has a real part that is exactly what we have defined as gamma in the within the this extra Markov approximation. So within the simple derivation that we made for the master equation originally. So this is already very interesting. Like it appears automatically in the infinite time limit. But now we get an imaginary part. And this imaginary part, it's very interesting. It's essentially the integration from 0 to infinity in frequency of the spectral density, but now instead of doing half the Fourier transform, what we have is that we divide by the pole, okay, by omega minus epsilon, okay? This is an integral that is not convergent in general, and what we get is actually the principal part of that integral. So I don't know how familiar you are with principal parts. I hope that you have studied complex analysis and then you know at least a bit about it. But for our purposes, when we say principal part of an integral, it really means the following simple thing. So this is the principal part, which means doing the integral, but skipping the poles. Okay, and I will give you in a second an example so you will see it. But it literally means that you just start integrating, and whenever you find a pole, instead of considering it, you just jump it and you continue integrating. Okay, so you remove the infinities that come from the poles. So we will call to this contribution in here, you will understand in a second why, we will call it minus shift in energy, okay? Remember that epsilon is the atomic transition frequency. So then minus delta epsilon is essentially this shift in energy. Yeah. So, yeah, and as I say, the important thing is that, okay, this is the imaginary part, that it's something that we missed when we made the approximation that the coupling is independent of the frequency. So if you allow me to use this expression, so we check what happens for long times, then the final form of the master equation looks like this. So the atomic state evolves according to, so in the interaction picture, evolves according to this expression. So what is this? This is just the same master equation that we found, okay? So at least the dissipator part is exactly the same, but we get a Hamiltonian contribution, okay? This Hamiltonian contribution that comes from the imaginary part of the rate, of the decay rate, this is usually called, and in particular in the atom, this Hamiltonian contribution is a sigma set. So it's a contribution to the atomic transition. And in particular, this is called the Lamb shift, okay, of the atomic transition. Okay, so there is a Lamb shift. So of course you may wonder, but how big is this shift? Is it so big that the atomic transitions that we have been working with for the hydrogen atom and so on make no sense? Or is it so small that why did we do all this? So what we are going to see now, so we are going to try to answer the question of how big this lamp shift is. Okay. We will try to answer this, but we immediately find a problem, okay? And this is a huge problem that was worth a Nobel Prize, at least partially. Well, actually a couple of Nobel Prizes, but in theory, one Nobel Prize. And it's the following issue. So we have, in our case, we have a spectral density, G of omega, that, as I say, is proportional to omega, okay? So then if you come to this expression for the lamp shift and you put here omega, then you see that you have a divergence, okay? Because the denominator is omega, the numerator is omega, and then you have an integration from 0 to infinity. So then you have what we usually call a logarithmic divergence, and we will see it explicitly in a second. So this means that in principle, this diverges. Okay, and you can imagine that this will be even worse in 2D. So it's worse in 2D, 3D, or other configurations that you can think of, okay? So what does this mean? This is really crazy because in principle, and it actually was a big puzzle, because in principle, this is telling you that the lamp shift is so big that you should not be able to see the atomic transitions that we see in the experiments, which makes no sense. Now the point is that these divergences that appear in here, in general, have to be dealt with. So in general, these divergences come from a few places. In our case, part of it is because we have done such a simplified model of the interaction between the atom and the light field, this dipole approximation. But even doing a full quantum electrodynamics model without any dipole approximations and so on, you will still find a divergence, okay? So, and in particular, so let me just mention that in order to calculate this lamp shift, in general, you need to do it using relativistic quantum field theory or quantum electrodynamics. So let's say QED, quantum electrodynamics. And that's not enough. You need to also add what is known as renormalization. Renormalization, which is a method or is the technique that is used in quantum field theory, and in particular in the standard model, to remove unphysical divergences, such as the one that appears in this lamp shift, okay? So in fact, so this lamp shift is so important that the reason why, or one of the main, let's say, evidences that quantum electrodynamics was correct is that once renormalized, you could see that the lamp shift that it predicted was exactly the lamp shift that was observed in the laboratory. Because, and that's what we are going to see now, this lamp shift, it's small compared to the atomic transition, but it's still large enough that you can measure it in the lab. And we are going, so maybe before we make the break, because this will not take very long, and then we finish the chapter, let's do a rough estimation. So as I said, if you want an exact calculation, so an exact number, then you really need to be careful and do it with quantum electrodynamics and renormalization. However, If we want to make just a rough estimation, we are going to get already something meaningful. And this rough estimation is the following. So just let's take for this estimation, G, instead of dependent on the frequency, let's take it as just independent of the frequency as usual, and let's call it gamma over pi. And let's impose an energy cutoff for the integral. And for example, let's call this energy cutoff, so to the frequency integral. We will call it epsilon, which is the atomic transition. So that's the point that we know that we have the main contribution of our environment. And then some scale that we will call lambda, okay? And lambda is an energy that will be much larger than epsilon. So then if we do this, we can actually evaluate the lamp shift, because we end up with this simple integration. So we have the principal part, and then the integration from 0 to epsilon plus the cutoff of d omega divided by omega minus epsilon. Okay, now this is where it comes the principal part. So the poles of this kernel, so of 1 over omega minus epsilon, is just epsilon, right? It's omega equal to epsilon. So when we say principal part, what we mean is exactly this. So we mean that we essentially take the integration from 0 to the pole, but just before the pole. So we are going to take a limit when h goes to 0, okay? And we are going to integrate from 0 to the pole minus that, that infinitesimal thing. So then we jump it, we jump the pole. So we start the next integral in epsilon plus h, and then we go all the way to the end of the integration domain. Okay, so this is exactly what it means, principal part. So you skip the pole. Now, so this integral is very simple because, well, you know what is the primitive or the integral of 1 over omega minus epsilon. This will just be the logarithm, right? So essentially we have limit when h goes to 0 of the logarithm of omega minus epsilon evaluated in the extremes. So in 0, h minus epsilon, h epsilon plus h, in epsilon plus the cutoff, and in particular you get this expression. Okay, the 4 contributions that you get are these ones. But now you can combine all these logarithms into one, and you get the logarithm of, let's start counting. So we get minus h on top, minus epsilon down, lambda on top, and minus h, sorry, and h in the denominator, okay? So just the sign in front of the logarithm tells you whether you are in the numerator or the denominator, and then we keep the sign of what we have inside the logarithm. So then you see automatically that this h goes away with this h, this minus with this minus, and then finally you get a logarithmic divergence. So we get this expression in here. Okay? So the important thing is to remember that the lamp shift, in our case, in this one-dimensional case, it has a logarithmic divergence. Okay? And whenever we have a logarithmic divergence, we know that this means because the dependence of the logarithm on the cutoff, it's very weak. So in particular, if you change by an order of magnitude or by 2 orders of magnitude, the cutoff, you will just multiply by 2 the logarithm. So it's not a big deal, okay? Then this essentially is telling us, and we are going to do some numbers now, that the lamp shift is actually of similar order as the decay rate. Okay? This is the takeaway message, which is that the lamp shift can be as large as the decay, okay? And this actually agrees with what is observed. So this is a very rough estimation, but still the number that you get is similar to what you get in the lab. So then let me just to finish give you some estimation for numbers. So in particular, just let's take, first we have to talk about the cutoff. So of course the cutoff has to be much larger than the atomic transition, but of course it doesn't make sense to have a cutoff that goes beyond, let's say 1 mega electron volt, which is the energy in which you start creating already pairs of electron and positron. Okay. Then on the other hand, for the hydrogen atom, so as an example, then the atomic transition between the first excited state and the ground state, so let's call it E2 and E1. So E1 and E2 refer to the principal quantum number n. So if you take this expression that we already discussed for the hydrogen atom, we get something like 13 electron volts. Okay? Then this automatically means if you take, so if you take the worst case scenario, the worst case scenario for the cutoff, which is make it as large as possible, let's say 1 mega electron volt, then what you get for this logarithm of cutoff divided epsilon, it's a very mild dependence. In particular, you get minus 3.5 gamma, okay? And for example, even if you consider hyperfine transitions, so let me just, so you see that the dependence is not too important, so the cutoff and so on. Even if you consider hyperfine transitions, which means that the transition is like 10 to the minus 5 electron volts, so it's 10 to the minus 6 times the one of the ground state of the hydrogen atom, then even in that situation, you only climb up to a lamp shift that it's minus 8 gamma. So as you see, you change 6 orders of magnitude, and it's still quite contained. So this is just to convince you that the lamp shift is a very much observed some effect that you can observe, that is highly important, and it was awarded 2 Nobel Prizes, one to Lamb and another one to the theorists. But still, the Lamb shift is very small compared to the typical transition frequency that you have in atoms and so on, okay? So you can neglect it for certain things, but you can also observe it, and that's very important. Okay, so I think this is a good point to make a recess. And if you have any questions, you can ask me after the recess or even now. And see you at 2:10, okay? 10 minutes. Okay, so welcome back after the break. And please, first of all, let me know if you have any questions about this chapter that you want to discuss now. Otherwise, as usual, you can always ask me offline. So if there is nothing urgent going on, then let's move on to the next chapter. I hope that this chapter was interesting for you in the sense that now you are able of deriving master equations for a system that it's not closed but open. So you know that there is life beyond Hamiltonian dynamics, okay? And that you know what are the approximations that you can do or that you need to do in order to be able to handle those dynamics in an easy enough way. But now we are going to move on to a very much related topic, which is now that we understand how to describe the system that is open, let's now try to understand how to describe and how to analyze the light that is coming out of that system, okay? How is the emission of that system, that open system? That's one of the reasons why we open the system in the first place, because we want to use whatever phenomena happens inside. We want to be able to extract it and use it for applications and so on, okay? So then let me just very schematically tell you what we are going to talk about in here. So what we have done so far is this theory in which we have a system. So either a cavity or an atom. And this cavity or atom, it's not perfectly closed. So they are not perfectly closed, but open. I went too far. Okay. And embedded in some kind of environment. Oops. Okay. So it's embedded in some kind of environment. So this is just what we have discussed. And what we have seen is that essentially we can make a theory in which the system evolves according to some Hamiltonian dynamics that we expect, and then some input. Some input that comes from the environment. Think, for example, on the Heisenberg picture approach, in which you have the input operators in the quantum Langevin equation. So, but what we are going to talk about now is what happens with the field that comes out of the cavity, so what we will call the output, okay? And that then is observed. So now we take this output and we have an observer. So this is the eye of the observer, okay? That has some kind of observing device, and then it's analyzing the field that comes out of the system, okay? So I do it very schematically here, but think that as we discussed, you can have several environments, and maybe the environment that you use to drive the system with a laser is not the environment that you are monitoring with an observer, okay? So you can have a theory of multiple environments in which some of them are to probe and some of them are to observe and so on. So this is pretty generic. And then in this chapter, what we are going to study in detail, so let me just enunciate it so you are aware of what we will do. So first of all, we are going to analyze a description, or I am going to give you a description of the output field. Okay. Then we will move on. So once we understand how to describe the output, what we need to learn how to describe is the observation. And in particular, we will talk about one specific type of detection that is very important in quantum optics, that is called photodetection. Okay. And through photodetection, we will talk about some phenomena that you might have heard of, which are bunching and anti-bunching. Okay. And then once we understand what is photodetection, we will see how using multiple photodetection, a scheme with multiple photodetection and laser sources, we can create some kind of other type of measurements, okay? And in particular, one called homodyne detection, that it's also super important in quantum optics. And this will connect with the actual use, practical use of squeezing. So we have already talked quite extensively about squeezed states, how to generate them with a Hamiltonian and how to describe them with Gaussian states and so on. But we haven't really talked about how it's squeezing used in experiments, okay? And this is what we will use this chapter for as well. So how to measure it, how to detect it, and what is it useful for. Okay, so this is what we are going to do. So then let me start with the first thing I promised, which is let's try to describe what is the output of a cavity. So we are going to do it first with example of a cavity, but you will see that it's very generic, very general. Okay, so we define the output field. So the output field, we define it as the part of the field, so part of the external field, that propagates towards, in the case of the cavity, towards the right, which of course is where we have the detector. So in a generic way, the output field is just a part of the external field that propagates towards the detector. Okay, in the cavity, because our partially transmitting mirror is the one on the right, is the field propagating towards the right. And we already know how to describe such a field. So in particular, the vector potential associated to that field, so we will call it A out. That depends on Z and T. This will be the polarization, the integration in frequencies, so integration over all modes, the normalization factor, then the annihilation operators of each of the external modes. Note that I'm in the Heisenberg picture, so this is for convenience, and it will be very important in this chapter to stick with the Heisenberg picture, at least at the beginning. And then we usually write down in here the standing wave outside of the cavity, but we care only about the part that is propagating towards the right. So then we have to put in here just that part. So just the part that is propagating with positive wave vector. And of course, because we have turned the sign into an exponential, we have a 1/2 that we can put inside the square root, okay? So this is the expression for the part of the field that is propagating outside of the cavity, okay, towards the detector. And now we just make one approximation that we could live without it, but it simplifies everything a lot, which is that, as usual, only frequencies that are around the cavity frequency contribute. Okay, and in particular, what this means for this case is that every function of omega that is slowly varying, for example, the square root of omega, okay, we just evaluate it at the cavity frequency and pull it out of the integration, okay? Because we know that only the part of the integration around the cavity frequency will contribute. We cannot do that with these two because they oscillate quite fast, okay? They oscillate at the frequency of the cavity. So we cannot do that. So oscillate with omega. But we can do it for the square root of omega, and we can also extend the integration to -infinity as usual. And then we are left with this thing in here. So we have 4 pi epsilon 0 CS omega cavity, and then integration from -infinity to infinity of b omega, and then b of omega t e to the I k z minus z. Okay? And then now the last step is just that from the previous chapter, we actually know what is the evolution of b of omega t. So we know the solution for b of omega t in the Heisenberg picture. And let me remind you that when we formally integrate the equation of the environment in the Heisenberg picture, what we get is that b of omega t is equal to the Heisenberg operators at time 0, and then multiplied by their free evolution. And then the part of the interaction with the cavity that we can write like this. This is t prime, then a of t prime e minus I omega t minus t prime. Okay? So this is the solution that we wrote formally in the Heisenberg picture. And if we take this and we just insert it into the expression above, so let me make it small, keep it here. And then if we do this, oops. So again, we use this thing. Then we can rewrite this expression as the polarization, the normalization, and now we have two terms, one associated to the initial condition for the external fields that we write like this, and one associated to the cavity field, so the interaction with the cavity field, which we write like this. So let me move this. A little bit here. And let me tell you what TR is. So just note that when we take minus I of omega t minus t prime, and we combine it with this exponential factor in here, okay. Oh, actually, yeah. This is also TR, and this is T prime, of course. I think I'm not making a mistake, minus I omega t, yeah. Okay, so this TR is just the factor, including the factor of the plane wave in the time. So it's equal to, so TR is just the time, and then you remove this Z minus L divided by C, which is the time that it takes for the light field to reach the detector, which is at position Z, okay? So from the cavity mirror, which is at L, is the time that it takes to go there. So then this is called the retarded time. Okay. Then now you see that this is very nice because, well, first of all, this object in here is something that we know from the previous chapter. This is what we call the input operator at time TR. Let me write time better. Okay. And this is just a delta function of t prime minus tr. Okay? So then when you put everything together, and we are going to make even one more, well, I will say it later because we don't really need it. So then if you see the final expression for the output field at position Z at time t, it's equal to just these prefactors in here. And then something that we will call the output operator. Okay, evaluated at time tr. And this output operator at time t, any generic time t, is just equal, or it can be written as so square root of 2 gamma, and then the contribution from the cavity minus the input. Okay, so you just need to write the things in here and you will find that expression. Okay, so the delta function removes the time integration and evaluates t at tr, so evaluates a at tr. So then you end up with this final expression here. And this is what we call the input output relations. So it sounds very fancy. We have done a quantum calculation that looks very cool and so on. But at the end of the day, this is nothing. This is a very trivial thing that we knew from the beginning. These are just the Fresnel relations. So it's just the boundary conditions of the mirror. So of course, if you combine the input and the output, that combines to the internal field. That's just the boundary condition, as I say, okay? If you want another way of thinking about it, is that the output field will be the cavity field, okay? The part that transmits, because this gamma is the transmission, okay? Plus the input field that has been reflected. So the part of the input field that is reflected from the mirror, that gets a minus phase, okay? So the interference of those two things, so the input, so the intracavity field and the reflected input field, that's the output field. So it's very, very intuitive, okay? And so this, yeah, another thing that maybe it's worth remarking is, why do I call B out to this combination and not to that combination with the factor 1 over square root of 2 or the C or the epsilon 0? So why do I define that operator? So as you are going to see now, this operator satisfies canonical commutation relations. So this operator, it's actually an annihilation operator, okay? So that's why, and it's this combination and not any other. So if you divide by square root of 2, then this is not an annihilation operator, it's proportional to 1, but this is not an annihilation operator. So that we will see in a second. And then the other small remark I want to make is that just note that usually, actually retardation effects are not very important. So first of all, because gamma t is usually infinity, so in the sense that we care about what happens for very long times, okay? But most importantly, because set is usually not too far from the cavity. Okay, so in total, this means that essentially you can approximate the retarded time by t, okay? So just imagine that if we are in the laboratory, we have the detector close to the cavity, and that's fine. So these retardation effects might be important for many applications, but definitely not for typical experiments. So it's just something that you need to keep in mind, but that we are not going to even discuss anymore because we will not require it. Okay? So then now we have a description of the output field. So the field that is arriving to the detector as a function of some operator that has a very simple expression in terms of things that we know. So the intracavity field that we know how to evaluate from the previous chapter, and the input operator that we have defined also in the previous chapter. However, it's also interesting to find an alternative form of the output operator that will actually allow us to prove the following properties that are super important. So we will now prove with this alternative expression for the output operator these two properties. So the first one, as I said, is that the output operators, just like the input operators, they satisfy canonical commutation relations in time. So these relations in here. Oops. Okay, so canonical commutation relations in time. So this is very important because this allows us to see, even if we are not going to use it very much in here, but it allows us to see that you can describe the state, okay, of the output field, so of the external field that you are measuring, as somehow a state for each harmonic oscillator at each time t, okay? And this is something that we already talked a little bit about for the input operator, that you can also define it as a stream, let's say, of states defined for each time t, okay? So, but we will not use this much. So it's just something that you have to keep in mind because it is used a lot in research of certain types. And now we are going to prove also a second thing, which is very important, which is that for any intracavity operator, let's call it C at time t. Okay, so Heisenberg picture, we have some operator inside the cavity at a given time t. We are going to prove that the commutator between this cavity operator and the input field at time t prime, it's equal to 0 if t, so if t prime is larger than t. So if the input operator is in the future of C, of the cavity. And similarly, we are going to prove that the commutator with the output operators, okay, this doesn't matter if we have the output operator or the dagger, okay, and the same for the input. So either B or B dagger, doesn't matter, because this is for any intracavity operator. Then this is 0 now when the output operator is in the past. Okay. And this is called causality. So this is amazing because, I mean, we didn't do a theory that incorporates causality explicitly, at least not on purpose, right? So, but however, our theory, so this kind of within the Markov approximation, within all these approximations that we have made that maybe would break causality in some limit that it's irrelevant for experiments or whatever, this doesn't happen. So we still have causality. So of course, the input field acts on the cavity, and therefore the cavity cannot depend on input in the input field in the future. Okay, so that's what this is saying. And for the output is the same. The output field comes from something in the cavity, and therefore it can only depend on things in the past of the cavity, not things in the future. So did I say it correctly? Yeah.
Sorry, but
yeah.
But I remember the input field is not a dynamical variable. I remember. Is that right?
Sorry, come again. I didn't hear.
And the input field, I remember, is not a dynamical operation.
Yes. Yeah. So it's a field that doesn't have dynamics, but still, in this picture that we have of inputs and outputs, okay. So imagine the following situation. Imagine that you forget about the system for a second and you care only about the environment, okay? Then what you have is that you know the input of your environment and you want to know the output, okay? So in that sense, the input is defined at a certain time. It's not dynamical in the sense that it doesn't have an evolution equation, but it's defined at a certain time. It depends on time. It's just that it's not a dynamical dependence in the sense that you need to solve an evolution equation for it or anything like that. You know what is the time evolution. It's just the Fourier transform of whatever initial state you have in there. But it depends on time. So at different times, it has different values, okay?
Yeah, that's true.
So then this theory is just telling you that the input operator at time t is related with the output operator at time t, and they are connected through a system in a causal way, okay?
Okay.
So that's all this is saying. But you are right, just like we discussed, the input is not dynamical in the sense that it doesn't obey some dynamical equation that we need to solve. It's a trivial object. And the output operator as well, once we know the intracavity operator, okay? That's all.
Okay, thanks.
Okay, so then let's prove this. And the reason why I do the proof is because we will find some interesting things along the way. So let's do the proofs. So for this, first I need you to remember the Heisenberg equations of motion for the full system and environment, which, if you remember, this is just exactly this. So this is the free evolution of the cavity. And then we have here the coupling to the external field. And then we have the evolution for the external field, which has, the free evolution. And then,
sorry, it seems the
yes.
screen got stuck. Gets stuck. I can't.
So let me
see.
start. Yeah, let me start sharing again. Your question broke the class. I don't know why. Causality, probably we are breaking some causality thing that the computer doesn't like. So do you see it now?
Yes.
Okay. So, and you see my laser, right? So it's updated at real time. Okay. Perfect. So yeah, what I was saying is that for the proof, the first thing I need you to remember are the Heisenberg equations for the open system. So this means the equation for the annihilation operator of the cavity and for the annihilation operator of the environment, which I just realized I forgot to put an omega. And then we have the free evolution and then some part related to the coupling. Okay? So let me just name this equation. So this one I will call it A and this one I will call it B. And then we are going to do the following. So first of all, we have already solved formally the second equation a few times. So in particular, what we have done is what I will here call the forward integration. So the forward integration of the equation for the environment, which means that we check what happens from t equals 0 to t towards infinity, subject to the initial condition. So we give an initial condition, which is that b of omega at time 0 is just b0 of omega. So this is what we have done so far. And in particular, this allows you to write b of omega t as b0 of omega e to the minus I omega t, and then plus square root of gamma over pi, integration from 0 to t, d t prime, then a of t prime e to the minus I omega t minus t prime. Okay, this is what we already wrote. However, this is a first order differential equation, and you can in principle solve it from any point in time that you want. So in particular, let's solve it in a funny way. That is what we call the backwards integration. Of B, which now means the following. Imagine that you are interested in some very long time that we call t. So that's your final time for the experiment. So you don't care what happens after that. So then we are going to integrate the equation now for times smaller than this final time. And we will then, instead of giving the initial condition, we will give the final condition. So we integrate the equation subject to a final condition. So, and we integrate backwards in time. So this is something that mathematically I can do. And we will call this operator BT omega, okay? So in particular, if you do that, mathematically, you will find something very easy, that is that B omega time T can be written as this expression here. So the final condition, and then minus omega T minus T, if I remember properly, and then square root of gamma over pi, integration 0 T, dt prime, integration from final time to the time that we want, but we invert, and then we put a minus sign, and we get dt prime, and then a t prime e minus I omega t minus t prime. Okay? So formally we can do this. There is nothing that tells us that we cannot do this. Even though it's a bit crazy because it's like you know the future and you want to now know the past. Okay, whatever. Okay, however, this is very interesting because now we have two alternative expressions for the operator, the external operators at time t. Okay, and in particular now we can play the following game. So we can now integrate, so do, let's say, yeah, the integration in frequencies. Okay, actually not 2 pi, but the square root of 2 pi. So if we just do the integration of this, and then we say that this is equal to this, okay, and we integrate, you see that the final solution or the final expression that you get is something like this. So you have a term that it's just the one of the final condition, and then integrated. Okay, and this is equal to what? So just take a look. When you do the integration in omegas in this term, so in the forward equation, the initial condition term, that's just the input operator, okay? And on the other hand, when you do the integration in omegas of the interaction terms, of the intracavity terms, then you see that you get delta functions because you are integrating in omega, and then you get the delta function of t minus t prime, okay? So this means that at the end of the day, this thing that I just wrote in here, it's equal to 2 gamma, and then the intracavity operator at time t minus the input operator at time t. Oh, but is this familiar? Well, this is the output operator by definition. I mean, but by the definition that we made in the previous section. So this means that this equation here, or this expression here, so this part, is an alternative expression for the output operator, okay? So it's not so important in the sense that we are never going to use this expression to evaluate actual physical phenomena. However, it's very important that now we have an expression of the output operator in terms of operators of the external field at some given time. Because now we can easily compute the commutators of the output operators. Since we know the equal time commutation relations of the external field. So at any time t, in particular at the final time capital T, we know that this is satisfied. So just like we did with the input operators but for 0 time. Okay? So you know that at equal times, the external operators satisfy these canonical commutation relations in frequency. And then this automatically, if you just use this definition in here, this automatically proves this part. So let me just copy it. It's easier than writing it. Okay. So you can do it yourself, but it's exactly what we did for the input operator. There is nothing special. And so this is essentially just to prove the commutators of the output operators. And now we can also do something similar. Well, not similar, actually, very different, sorry. But we can use these equations. So these equations, these Heisenberg equations and the forward and backward integrations to prove the causality relations, okay? So I show you how to do this. It's again very easy, and it's really as intuitive as what I mentioned before. So it's just, so let me come back now to the equation A. So in particular, what I mean by coming back is that now we have the formal integration of the external operators at time t in 2 ways, forward and backward. So now we can substitute it in the equation A and find a dynamical equation for the intracavity operator A. So of course, when we put the forward integration, we will get just the quantum Langevin equation that we know. But now what's interesting is also what happens when we put the backwards integration. So what do we get? So let's see it, and you will see that it's actually quite interesting. So if we use the forward quantum, so if we use the forward formal integration of the external modes, then what we will get is something that is called the forward quantum Langevin equation, okay, which is for t larger than 0. So for, let's say, t going into the future, and it's what we have already seen. So it's just that this is equal to losses, free evolution, and then we have an input operator that is driving the cavity. And of course, as I say, we go into the future from some initial condition A of 0. And what happens when I put the backwards one? So if I put the backwards formal integration of the external modes, what I get is what is known as the backward quantum Langevin equation that goes into the past from some, let's say, final time t. And the equation looks like this. So it's very funny. Now we have plus gamma. And I think we have minus I omega c still. Yeah, of course, because that comes from the equation itself. And then minus the square root of 2 gamma. And now we have the output operator instead of the input. And this, you have to solve it from some final condition that you know. Okay? So this is the formal quantum Langevin equation, but going into the past. Okay? So if you would know the state at some time t, and you want to know what happened before, and you know how is the output operator, then you have all the information to know what happened before. But then this is very interesting, and this finalizes the proof, because now A of t, so according to the forward Langevin equation, it depends only on the input operator for times smaller than t. Okay? And similarly, from the backward Langevin equation, it depends on the output operator for times in the future of t. Okay? So AT, let me repeat it in a different way. At time t, A doesn't depend on the input operator in the future. Okay? And it doesn't depend on the output operator in the past. Okay? Now, because you know that the input and the output operators satisfy these canonical commutation relations, okay? So in particular, they commute at different times, okay? So if they are not at the same time, they commute, then this automatically means that if you take the commutator of A of t with B of t prime larger than t, this is equal to 0, okay? Because you will have the commutator of B in the future with B in the future with B in the past, okay? And that's equal to 0 because they are at different times. And then the same happens with, if you take A of t commutator with B out in the, so when t prime is in the past. Okay? So you don't need to do anything else for the proof. This is a first order differential equation, so you automatically know that A of t depends only on what happened before t, because this is a time local first order differential equation. And the same for the backwards, only that now you are solving backwards in time, okay? So this basically gives you the proof and shows some interesting expressions of the output operator in terms of final times. And it allows you to see also what is the inverse of the Langevin equation that we saw in the previous chapter. Okay? So I hope that this is kind of interesting, but now we have a theory of inputs and outputs that preserves causality and that allows us to see the quantum state coming out of the cavity as a stream of states for some annihilation operators or some modes, some harmonic oscillators that we call output harmonic oscillators, and you can define at each time t, okay? So that's all. So I think that this might be a good moment because we will move now. No, I tell you very quickly about the output radiated by an atom, okay? So you can do the same now. Instead of for a cavity with a partially transmitting mirror, you can do it for an atom in free space. So let me just show you very quickly kind of the intuitive idea about this. So you have the atom, and as we have discussed already a few times, we have part of the field that propagates. So when it emits, for example, part of the field that propagates towards the right and part of the field that propagates toward the left. And now what's interesting is that the observer, so in principle, detections are local. I mean, if you have a photodetector, the photodetector measures whatever comes into the photodetector. But in an atom, this means that with a single photodetector, you can only measure half of the radiation that comes out. And this will show up in the expression for the output field. So in particular, if you repeat what I did for the cavity, but for the atom, so the detected output field, now you can write it very similarly. So is the output at position set t will be equal to, again, the common prefactor to C epsilon 0 S, and now we make the approximation that this is the transition, the atomic transition. And now we have an output operator. Evaluated at the retarded time. So again, the time it takes for light to go from the atom to the detector. Now, well, the time minus the time, so retarded by the time it takes for light to reach the detector. And this output operator, funnily enough, it's equal. So it's still proportional to the so the operator of the system, which is in this case the lowering operator of the atom, minus the input operator. But now instead of square root of 2 gamma, we have only square root of 1 gamma, okay? And the reason is because half of the radiation is not coming into the detector, it's going away. So then that part, you don't see it, okay? So let me just write it down. So this is half the one of the cavity. Because we are missing half of the emitted field. So nothing special, okay? So then we also have a theory of inputs and outputs for the atom, for an atom in free space. And in general, you can do it for any system interacting with an environment that you like. So then now we will make a break, and after the break, then we will start discussing how do we observe the output, okay? And in particular, the theory of photodetection and something called correlation functions. So let's maybe meet in 8 minutes to make it round, like at 3:10, okay? So see you in 8 minutes. Okay, so let's start now talking about photodetection. So first of all, let me tell you what is a photodetector or how photodetection works. And what I am going to say is quite general, but as you can imagine, like technology of measuring devices like moves very quickly, and in the last decades and so on, it has advanced a lot from what was at the beginning. We have now the opportunity of doing many crazy things that we didn't think that we would be doing, but at least the very basic core technology of what I am going to explain, it's always something based on the photoelectric effect. And then I am going to give you a theory of a photodetector with a based on the photoelectric effect or some variations of it. So let me just start in the following way. So let me give you just the sketch of how a photodetector works. So we start from our system, that can be the atom or the cavity or any other quantum optics system. And then the system has some kind of output, okay? Let me change the color. So we have here some output. Okay, and then the detector starts. So what is the detector? So the detector essentially starts always with some kind of a metallic plate. So it could be something different, but it's something that has weakly bound electrons. Something that has weakly bound electrons, such that when a photon, so this is a photon, hits it in one point, it can release electrons. So in particular, one photon can release one electron, like we know from the theory of the photoelectric effect. And now it comes the funny part of a photodetector. So of course, now that we have transformed one photon into one electron, in principle, we can measure the electron, like we have an electric current, but it's an electric current of one electron. So that's so microscopic that it's not really easy to see. So then what we do is that we now put here some metallic plates, sorry, some plates at different voltages, in particular at increasing voltages, okay? So this is a stage with plates at increasing voltage, what we could call an amplifier. So this is a current amplifier. So it takes one electron, and now what's interesting is that, of course, because you are accelerating this electron, it gains energy and goes towards the plate, but then it hits the plate, and when it hits the plate, it releases even more electrons, okay? And then when these electrons hit the next plate, they release even more electrons, okay? And so on. So then at the end of the day, starting from a single electron, we actually create what we will call a photopulse or an electronic current, an electronic pulse made up of many electrons. So a macroscopic number of electrons that now we can measure. Okay, so this is called the photopulse. So it's an electronic pulse, an electric pulse current that has been generated by a single photon. Okay, then essentially these photopulses, so each photon will create one photopulse, and this photopulse will just move on, and essentially this is the fundamental description of the photodetector. Photodetector. Okay, and now once you have the photopulses and you add all the combination of photopulses, so of all photopulses, this creates finally a current that depends on time, okay? So you are sending light into the metallic plate, the light has photons, and just randomly, according to the photoelectric effect and the probability laws of quantum mechanics, some electrons get released, and each of the electrons that get released creates a cascade that is a photopulse. And then all the combination of photopulses creates a macroscopic measurable current. So this is a macroscopic measurable current that we call the photocurrent. that now it's continuous in time. I mean, for every time it will have a value and it will be fluctuating, it will be changing. Okay? So this is the basic, like the most sketch way of telling you what is a photodetector and how it works. And the most important idea that I want you to get is that starting from a quantum field, okay, with some distribution of photons in time and so on, so just a quantum field described by quantum field theory, you do some magic in something called a photodetector, and you transform that field, that quantum field, into a macroscopic measurable current. And what's important about this current is that it's a fluctuating current. So it's a stochastic signal, okay, that it's random in the sense that you don't know how many electrons will appear at a specific time, of course, because it depends on all these kind of random processes of how many electrons are released after the collisions. It depends also on this kind of random process of the photon absorbs the atom or the electron absorbs the photon or not, and things like this. So you know it's a stochastic signal, but you transform quantum fluctuations into classical fluctuations, okay? So this is the important point. So the photocurrent J of t, this is a stochastic signal. Okay, that is built up from, so it's stochastic because it's built up from random photon absorption and electron collisions. Okay, and what's really magical and is really interesting is that the fluctuations of this stochastic signal encode the fluctuations, the quantum fluctuations of a quantum mechanical operator, okay? And this is what I want to write in here. So in particular, I want to say that it encodes the quantum statistics of one quantum mechanical operator that it's maybe the one that you have in mind. It's just the number operator. The number operator of who? The number operator of the output field, so of the whole field. So this is why we define the output field as well, because it's the operator that matters in the detection. And in particular, when I say that it encodes the quantum statistics, what I mean in precise terms is that the stochastic moments of this current so if you consider the moment of order n or the time correlation function of nth order, so this means that you just check at time t how are the fluctuations of the current, and then you just do the average between the multiplication of the current at times t1, t2, tn, etc. This is proportional to the same thing for the quantum expectation value of this operator. So the number operator of the output field. And very importantly, in normal order, okay? So these two dots, I think we have talked about them, but I don't think I introduced the notation of two dots. So this notation of two dots, it means that you just take whatever you have inside and you put it in normal order without using commutation relations or anything. You just literally, if I give you A dagger, you just change it to A dagger A. And so I remind you that normal order means that annihilation operators to the right and creation operators to the left. So I will give you one example in a second, okay? But this is kind of the important result of photodetection theory. And the only thing, this is one of the few things that I will not give you a proof of, you will not even have it in the notes, okay? Is that the proof of this thing, okay, is highly non-trivial. So it requires a bit of work. It's not super difficult, but it requires a few smart ideas and then a lot of work, okay? So, but for here, the only thing that we will need is that you believe me when I say that the statistics, the stochastic statistics of this photocurrent encode the quantum statistics of this photon number output operator. And just to give you one example of this normal order, so we will always assume also that T1 it's smaller than T2, which is smaller than Tn, okay? And this is always possible. I mean, I am not making any approximation or assumption, crazy assumption in here. This is always possible because I remind you that the output operators at different times commute, right? So if you don't have them in chronological order, you just reorder them. So that is, so in particular, if the number operators are not in chronological order, then you just reorder them because they commute. So T prime different than T, this commutes. And this works as well if you put here the dagger, so it doesn't matter. Then, for example, if I give you an expression like this, I tell you what is the normal order of the multiplication of two output operators, two output number operators, okay? And imagine, so assuming that T1 is smaller than T2, yeah? So what do? First, we have normal order. So, well, we have time order, which means that we will always assume that T1 is on the, so let me see if I'm doing it correctly. Yeah. So that T1 is on the left of T2, according to this expression. And now we have to order it. I think, so I am not being precise enough. So we will assume always that T1 satisfies this. And I have to tell you one more thing. So we will assume this and use time order. Time or chronological order. Okay. So remember that time order, we defined it already. And what we were saying is that in time order, annihilation operators at a later time appear to the left of annihilation operators at an earlier time, okay? And the opposite for creation operators. Then after all, if we have this situation in here in which T1 is smaller than T2, and we have the normal order of n out of T1, T2, then we can always write it as B out of T1 dagger, B out dagger of T2, then B out of T2, sorry, and B out of T1. Okay? So this is what this expression means exactly. So we will always have that the nth order correlation, time correlation function of the photocurrent, it's equal to the normal and time order version of the multiplication of the corresponding photon number output operators. Okay? So I hope this is clear. And then we have 12 minutes left. Yeah, so maybe I just give you one more thing and then we will continue next week. So now what I want to, so I know this feels a little bit dry, like, okay, so you will have this and so what? So what are we going to do with it? So now what I want to do in the remaining part of this section is that I will just tell you what is then the most general kind of object that we can measure with a photodetector or with a combination of photodetectors. And these are called correlation functions, field correlation functions. And they play a very, very important role in quantum optics because it's the observables that we have access to. So on the way to define that, let me first of all use a combined notation for all the systems that we have studied, so the cavity and the atom. So let's combine the notations for the cavity and the atom, because we will use it a lot now, like some kind of combined notation. And most things we have already talked about, so we will call system to either the cavity or the atom. So the cavity, the atom, or any other open system that we are working with. Then we will denote the operators that create transitions, okay, in the free energy, so in the free Hamiltonian of our system, we will denote them by S. And this means that it's the annihilation operator for the cavity or the lowering operator for the atom, okay, and so on. Then we will call environment, as we have already done, to what we define as the environment for our system. In the case of the cavity, is just the external field. In the case of the atom, is the field in free space. And so on. Then we are going to define a rate kappa. That is just the rate that appears in the input-output relations, okay? So this means that for the cavity, this is a 2 gamma, and for the atom, it's just a gamma because we are watching only half of the radiated field. So in particular, this means that the output operator in the open system we are interested about, this can be written in this combined notation as square root of kappa system operator S at time t minus the input operator at time t. Okay? So this is completely, it's just a notation. So just to combine everything together. And we are going to define one more thing for this chapter that will be very useful. So remember that in the Heisenberg picture, when working in the previous chapter, instead of working with the operator B in, so the input operator B, we were working with an input operator that we call A, right? Which simply was the input operator to which we remove the coherent or the laser part. So we are going to do the same for the output operator because it's very, very useful. In particular, we are going to remove from the output operator that part of the input operator. So in particular, we will define A out as the same expression with input-output relations, but with the A operator in the input instead of the B operator, okay? So if you want, in other words, the real output field is just the A output minus the laser part of the input, okay? So let me write it explicitly. Laser injection discounted. Okay, we discount the laser injection. Okay, so then now, if you imagine that you have photodetectors that are sensitive to this kind of correlation function, quantum correlation function, and now you can play with lasers and with many photodetectors, okay? Then I will convince you during this chapter, but hopefully you are already convinced because it's quite obvious that the most general correlation function that you will be able to evaluate, or in general, let me put it this way, that you will always be able to design an experiment in which you evaluate a correlation function that we will call G out Mn of times T1, T2, up until Tn plus m, so n plus m times, that it's just the following. So it's the A dagger out at time T1, then at time T2, all the way until time Tn, and then A at time T n plus 1, so another independent time, times time n plus 2, and then all the way up to time n plus m. Okay? This is the most general object that we can measure in an experiment that involves just photodetectors and the possibility of combining our output with other lasers. So these are called field correlation functions. And we will always assume in these correlation functions that T1, so this kind of chronological order or time order. So this one for the annihilation operators, and this one for the creation operators, and this one for the annihilation operators. So as I said, this is something that we can always do. And essentially, these field correlation functions are another part of what gave Roy Glauber the Nobel Prize, okay? So it looks very simple, okay, it's just a definition, but what Roy Glauber realized is with very simple arguments, he was a very smart guy, is that these quantum observables, these quantum correlation functions, are the ones that determine everything about experiments that people were doing with lasers, photodetectors, thermal light coming from the stars, and correlation experiments with photodetectors in general. And these, together with using quantum electrodynamics and defining coherent states and thermal states and all these things, this gave Glauber the Nobel Prize and, let's say, started all the business of quantum optics, and understanding that second quantization, it's important for the description of optics experiments in certain regimes that we can call quantum optics, okay? So then these correlation functions that are so important in quantum optics is what we are going to care about for the rest of the chapter. So for the next couple of classes, which are the last classes basically. And you will see that the interpretation of these correlation functions, we will learn about it, and we will see that they are very important for very obvious reasons and physical reasons, not only because they connect with experiments, but because they have physical meaning that is very relevant. Okay, so I think that this is all I will say for today, and I will tell you more things in next week. So as I said, I will give you a final exercise maybe later today, and after that I will give you more exercises, but you don't have to hand them in. It's just for you to know that these things exist. But this will be the last exercise because I don't want you to be doing exercises right until the exam. I prefer that you have time to study. Yeah. Okay, so if anyone has any question, now is the time. And we have maybe just a few minutes. Otherwise, as usual, I just say goodbye and you can start going away.